Yeah, so next we have Patrick from University Montreal, and yeah, so the talk will be evaluating the effect of variability in biomass burning emissions inventories on model PM2.5. And I think that can also answer some of the questions which people have. Okay, go ahead, Patrick. Thank you.
Great. Thank you, Yang. I want to start by thanking all the organizers for giving me the opportunity to share my research and to talk a little bit. It's been really interesting. I think actually it's really great to go after Yang because she gave an awesome introduction to chemical transport models, but then also some of the questions that came up are questions we're also looking at in our research as well too. So the program is working out really well, which is very exciting. So I'm going to talk a little bit about fires in Canada specifically. And so the here, and I think I can do a pointer here. Very great. So I think you can see can you see my laser pointer?
Yes, we can.
Okay, great. So in Canada, obviously we're impacted nationally by wildfires, but I kind of want to reinforce the point that Canadian wildfires have a global impact. So I have some statistics here from Natural Resources Canada, but Canada, of course, is a very large country. And so 9% of the world's forests are found in Canada and 28% of the world's boreal forests are found in Canada. So, we're talking about, if there's a fire in Canada, a large fire in Canada, it really has global impacts on both the forest ecosystem as well as the atmosphere. And so to emphasize this point here, I'm showing some data on area burned. And what we can see here is the area burned in hectares. And for each year between 1990 and 2021. And we can see in 2021 that approximately 4 million hectares were burned, and that's equal to the size of Switzerland. So we're really talking about massive fires that occur in Canada. And so this is actually 2021. This is the same year that Yang was talking about in the first part of her talk. And so if we want to understand the health or the climate impacts of these fires, one thing that's important to use as chemical transport models. So it's a useful tool for understanding the impacts of these fires, as Yang already explained. She talked a little bit about the health impacts, and one thing that I think is really interesting is also the climate impacts as well too, in terms of the direct and indirect radiative forcing. So what I'm showing here on the right is a figure taken from a paper published by Therese Carter and call it HELD, where they compared emission inventories, so 4 emission inventories, GFED, FIN, QFED, and GFAS for boreal North America and the continental US. And they look specifically at the emissions of organic carbon and black carbon. So these are the 2 principal components of PM2.5. And what you see is when you look across the different inventories, there's actually really large differences in the emissions of these components. And so then when you take those differences and then you do a radiative transfer calculation, what you see is the radiative effects of the aerosols actually change a lot too, depending on which inventory you're using. So you see essentially for organic aerosol where the radiative effect is negative, you see a factor of 2 difference in boreal North America and a factor of 4 difference in continental US, depending on which inventory you're using in your model. And so this is kind of gets to this problem, okay, if the choice of inventory is going to have a really large effect on the calculated radiative effect. Also, of course, on the health effects as well too. So it's kind of this underlying uncertainty when we want to use chemical transport models to understand health or climate impacts. So this is kind of another way to kind of get at the same idea where I'm showing geochem simulations for 2021. So this is kind of like Yang's, except we're looking at north of the border rather than south of the border. And we did it with 3 different inventories, so QFED, GFAS, and GFED. And what you can see is with spatial distribution, they're similar between the 3 different inventories, but there's really pretty large differences in the amount of PM2.5. And that's indicated by the color scheme, where I see much darker colors for GFED than you see for QFED. And also another kind of subtle difference here is it seems like GFED is better at picking up some of these smaller fires on the West Coast as well. And so again, this is kind of reinforcing the point that, okay, well, the emission inventories seem to have a fair amount of variability. And so, you could ask, the natural question to ask then is, this is kind of a straw man question, but like, what is, the best inventory? I don't think you can really answer that question necessarily in a way that's global, but it's kind of something that comes to mind when you look at this variability. And so, so I'm kind of coming at this from more of a data user than someone who develops inventories. And so, and also coming from the viewpoint of someone who does modeling and uses the inventories specifically in geochem. And so in this talk, I'm going to be talking about GFED, GFAST, QFED, and FIN a little bit. And I picked these inventories just because these are the ones that are usually used in geochem. Okay, so I know there are other inventories out there as well. And so I went through the literature on these different inventories, and this slide essentially summarizes some of the differences between these inventories. And again, I don't pretend to be an expert in inventory development, so I apologize if maybe there's some things that are wrong here. But for me, this is useful just as a modeler to understand, why are these inventories giving different emissions. And so basically with GFED and FIN, these are these so-called bottom-up models where we're using burned area or fire detection of hot spots, and then you calculate the fuel loadings and the amount of fuel consumed, combine that with your emission factors and speciation profiles, and then you get your emissions of all your different compounds. Whereas GFAST and QFED, these are top-down models where we're using fire radiative power and then this emission coefficient alpha to relate the fire radiative power to an emission. And so that's so that's really important differences between these inventories and probably explains the reason why they're different. Another thing is, if you go through the literature for these inventories, they are getting their emission factors from different articles. So there may be some difference there as well. And there's also some differences in the temporal resolution, the sensitivity to small fires. Also, these fire radiative power methods, they only detect fires during the burning phase. So, for example, if there's a cloud, it's not going to directly measure the fire activity underneath a cloud. And so then there'll have to be some sort of reconstruction or assumption that's made to kind of fill in that gap. And then also another thing that came up yesterday was, some methods are going to lack information about peat fires and burn depth for peat fires. So these are all different things to consider, when we talk about emission inventories and why they might produce a different result in a model like geochem. So there is one more inventory that I want to talk about, and that's this inventory CFEPs. And I think actually there's a talk a little bit later by Rodrigo Munoz Alpizar, who's going to talk more about CFEPs. So I hope I don't steal too much of his thunder. I get this all right. So CFEPs is essentially an inventory developed by Environment and Climate Change Canada for their air quality forecasting model, GEMMOC. So GEMMOC is the operational air quality model in Canada. It's used to give air quality alerts and notifications if there's going to be bad air quality that's forecasted for a given day. And this is and the way this model works, this emissions model works, is summarized in this figure here. And this figure is taken from a paper published recently by Carrie Anderson. So it's just been accepted in GMD. And so I just took and copied and pasted that figure from his article. So, well, essentially the way the CFEPs works is that it starts here with burned area mapping. And so it detects hotspots using MODIS and VIIRS and also AVHRR. And then it combines that with some climatology on burned areas and statistics on burned areas. This is historical data to estimate a burned area for all the hotspots. And that burned area is then fed into the CFEPS model. And then at the same time, there's this fire behavior system, which is quite interesting, I think, for modeling air quality, where they use current weather and fuel data to then predict how much fuel is consumed. Okay, and so this fire behavior and fuel consumption is then calculated on a per unit area basis. And this is interesting because this is going to vary dynamically depending on weather conditions. So things like temperature and humidity and precipitation will affect the fuel consumed. And it's my understanding that the other global emission inventories are not able to do that. And so then that goes into CFEPs as well too. And then we get the smoke emissions and the species emissions. And then there's also a really nice plume rise model as well that's incorporated in CFEPs that's based on Carrie Anderson's work in 2011 in this paper. So this is a thermodynamic plume rise model that uses the energy from the fire and the local forecasted meteorological predictions to simulate the plume rise. And so we get the emissions vertically distributed. So in this context, like, the goal of the project really is to compare CFEPs against these other inventories and see if these features of CFEPs improve forecasting of PM2.5 and black carbon. And so there's kind of a scientific question here, which is how does CFEPs compare against these other major inventories? We're going to use GeoChem sort of as a platform to answer that question. There's also kind of a technical goal as well too, is we want to take CFEPs and we want to put CFEPs into GeoChem for other people to use. So there's kind of a technical aspect as well too, because CFEPS was originally conceived for GenMach, and GenMach is mostly a closed model. So you essentially need to be a Canadian government employee to use the model. And so by moving CFEPS over to GeoSChem, which is an open model that's used by university researchers worldwide, we can sort of offer this this emission inventory to other research in a way that's more easily accessible. So for the methods, this is kind of summarizes how the inventories interface with the GeoSChem model. So we have the 4 inventories that we want to test for this project here, evaluate for this project. And then those are fed to GeoSChem through HEMCO, which is a harmonized emission component of the model. And what this does is it basically takes these different inventories and treats them in such a way that then they can be interpreted by GeoSChem and used in the chemical transport model. And so, for example, one thing it does is it takes these emission inventories and then regrids them onto a grid that will function with GeoSChem. The model parameters we used are summarized here. So we're using version 14 of the model with a full chemistry simulation. In this case, the model is being driven by MERA2 meteorology, and we focused on this 2021 period, which is quite interesting for studying wildfires that was already mentioned in Yang's talk. And then we're using a nested simulation. So the high resolution domain, which is shown here in this figure on the right, is at 0.5 by 0.625 degrees. And then there's also a global domain at 2.5 degrees. And then we have a vertical, we have 72 vertical layers in the model as well too. So the emission inventories we used were, as I already mentioned, GFED, GFAST, QFED, CFEPS. I want to add a little nuance here, which is CFEPS is the Canadian Forest Fire Emission Prediction System. So it actually covers Canada and the United States and a little bit more than that, but it's not global, this version of CFEPS that we're using. And so for the global domain, we're using GFAS to kind of fill in the global domain where CFEPS doesn't cover. I do want to add that this is the version of CFEPS we're using that's kind of limited geographically. There is a GFEPS, which is the Global Forest Fire Emission Prediction System, which is the global analog of CFEPS. Eventually, we want to also port that over to GeoSChem as well too, but that's for another talk in a year or so or something like that. So there is the possibility to go global with the CFEPS GFEPS model, but that's not what I'm presenting today in this talk. So for for implementing CFEPS, we start off with the emissions in a CSV file. Those emissions are then rasterized to go into a grid cell, and then we convert from CSV to NetCDF, so it's compatible with HEMCO and GeoSChem, and we sum the emissions from all the hotspots that are in the same grid cell, like as is shown as here. So one thing that's tricky here is that each hotspot has a plume height in CFEPS, and when we average all these hotspots into one grid cell, then we have to average the plume heights, and we weight that average based on the CO emissions. So there is some averaging of the plume heights that's done here. And then another thing that's I won't get into the details of this today because it is a little bit tricky, but we basically have to convert the GenMach species into the GeoSChem species. So there's some translation that has to be done there as well. One thing I want to mention quickly is GeoSChem, we're not calculating plume heights. We just kind of ingest that information from the emission inventory. So, and I'll talk about that more, in fact, on the next slide. And so in GeoSChem, we have these different options for the emission inventory. And in fact, the plume rise in GeoSChem is treated differently depending on the emission inventory that is used. And it's really drastically different depending on what inventory is used. And so for QFED, for example, it's pretty crude, I would say. So you basically, what they do with QFED emissions is they take 65% of those emissions and they go between the surface and the height of the planetary boundary layer. And then the other 35% goes between the PBL and 5,500 meters. And GFAS has a plume rise algorithm that's similar to the CFEPS algorithm, and that is actually used, and the maximum injection height is used from GFAS, and a mean is calculated. And then the emissions are evenly distributed between the surface and the mean altitude of maximum injection height. For QFED, we're still not entirely sure about this, but looking through the code, and this is one of the situations where I'm happy to get feedback from people, it seems like GFED is just emitted, the emissions are just emitted at the surface. And that's consistent with what we see in our comparisons to observations. So that surprised us a little bit because it seems like a pretty crude approximation, but that seems to be what is the case. And then finally, for CFEPs, it's analogous to GFAS. So there's basically an injection height that's calculated following the work of Carey Anderson, and then we distribute those emissions evenly between the surface and the injection height. One thing I want to mention here, and this is more of a technical point for other people doing geochem modeling, there is a bug in HEMCO that produces a low bias in the injection heights used for GFAS. And so it's not our group that found this bug. This has been something that several groups that have noticed and are working to correct. And this bug has also affected CFEPs as well too. We have corrected that. And so we have corrected versions of GFAS and corrected versions of CFEPs. And I'll be showing those in my talk today. So you'll see GFEPs C, CFEPs, or GFAS C, CFEP C, and that just means these are the versions of the emission inventories that have been corrected for this bug. So I'm happy to talk about the bug more offline, but it's very technical, but it does create basically a low bias in the injection height. So we compared the GSChem model against a variety of observations taken by the NAPS system. And so the NAPS system is the primary air quality monitoring system in Canada. And here we've used 74 NAP stations with PM2.5 data available in 2021. There's actually more NAP stations available, but in terms of just data management and having a kind of an equal distribution of stations, we culled some of the stations from the comparison. And so we use these 74 stations for comparing against the different geochem versions. And then one thing we also did was we looked at model performance for the western portion of the country versus the eastern portion of the country. And to define those two regions, we simply drew a horizontal line down the middle of the country like shown here. So this is west and this is east. Before getting into the comparison of the model with the observations, we did just quickly check beforehand how the emission ratios relative to CO compare to other inventories. So basically comparing this ratio for CFEPs against the same ratios for other inventories. And so here we see this ratio relative to CO for a variety of different species. Here, probably the most important things are the organic carbon and the black carbon, which are the principal components of PM2.5 in smoke. And then the different colors correspond to these different inventories. And what we see is that CFEPs, it's a little bit on the low side, okay? So it does tend to be lower than most of the other inventories. It's close to the QFED inventory, but it's not crazy, so it's not, it's not totally wildly out of line relative to the other inventories. So we know that the differences we see are probably not related to the speciation of the emissions. It's the differences we see are probably due to other things. And this is kind of true for, we're really focusing on PM in this talk, but this is true also for the other species like the VOCs and also for ammonia and nitrogen oxide and things like that. Okay, so here are some results where we're looking at the mean bias air for, here I have CFEPs, the corrected version of CFEPs, GFAS, the corrected version of GFAS, and GFED and QFED. And so what we see is for CFEPs, it's pretty good. So there's a slight positive bias at stations in Eastern Canada, but we can see here that the bias tends to be pretty low. And there's not much of a spatial gradient here. So there's no sort of geographic bias that's occurring. When you look at GFAS, it's also actually doing quite well. There's this region here that has a negative bias. I'm not quite sure why, so I can't explain that. QFED also does pretty well, but has a couple stations with a strong positive bias. Again, this is something that I can't explain right now. And then finally for GFED, what we see for GFED is there are multiple stations here kind of in the center of Canada where there's a strong positive bias. And this is most likely coming from this plume height issue where all the emissions are being emitted at the surface, because here these are stations that are basically directly downwind of fires that were occurring in this area of Canada. It's kind of like central and western Canada. So these would be the most affected by a plume height bug that put the emissions too low in the atmosphere. So I think that's what's causing these positive bias that we see here in GFED. So another way to look at the models is by looking at Taylor diagrams and violin plots. And so up here I have the Taylor diagrams. I'm just going to explain these quickly in case some people in the audience don't know how to look at these graphs. But essentially what we have here is the radial coordinate here, which corresponds to the correlation coefficient going from 0 to 1. the we also have sorry, this is the polar coordinate, my bad. So we have the polar coordinate here, which is the correlation coefficient. We have the radial coordinate, okay, here, which is the distance, and that corresponds to the standard deviation. And then we have these contours here, which are the root mean standard deviation. So this is a measure of essentially of the precision. And what we have here is the star. It's a little hard to see, and that's the observations, with a given standard deviation. And of course, the RMSD would be 0. And then we have the model predictions that are given by the different colored circles here. And so we see it's for Western Canada, the purple, so GFAS, corrected GFAS, corrected CFEPs, QFED, they're all doing about the same. Okay, so it's, so they're all having kind of a similar level of performance. The uncorrected CFEPs is quite far off because of probably this plume height issue. And again, GFED is quite far off too as well, again, because of plume height. When you look at Eastern Canada, there's a little bit more spread between these models here. So GFAS again seems to be performing the best, but QFED and CFEPs, once corrected, are doing pretty good as well, but not quite as well. And then GFED again is sort of out on its own here. We also look at the violin plots where we essentially see the distribution of concentrations of PM2.5. So we can look at, you can look at the different, 25th percentile and the 50th percentile and the 75th percentile, but maybe for the purpose of this talk, we can just look at this kind of smooth distribution here of the violin in the plot. And what you can see here is that, for Western Canada, CFEPs does produce this distribution quite well, as does GFAS, corrected GFAS. Whereas QFED and GFED, they're not quite as good. So QFED, the distribution is definitely biased a little low, and then GFED, the distribution is biased high. When we look at the eastern portion of Canada, the GFAS and the observations have a very similar distribution, so corrected GFAS here, whereas CFEPs tends to be biased a little high along with this GFED and QFED as well. So here it seems like in Eastern Canada, there is some sort of geographical dependence where something in GFAS is working better in Eastern Canada. So that makes GFAS a slightly better inventory for Eastern Canada. So then also I wanted to talk a little bit about black carbon. I think I have a few minutes left. I think I have about 3 minutes left according to my timer. So I just want to talk quickly about that as well too. Here we're seeing essentially this. The first thing I should say is there's a lot less black carbon measurements in Canada than PM2.5. So in the end, we thought we were going to have more data, but at the moment we only have data at 4 NAP stations for black carbon. So we're kind of looking at alternatives maybe for filling in this missing data set, but right now it's pretty limited in terms of the number of observations. And so what we're seeing here is for these 4 stations, the mean bias error for corrected CFEPs, corrected GFAS, QFED, and GFED. And what you see, it's pretty, in terms of the mean bias error, it's pretty similar for these 4 versions of the model and black carbon. When we look at the Taylor diagrams for these 4 stations, so Montreal, Hamilton, Ontario, Edmonton, and Vancouver, we get a little bit more distinction between the different emission inventories. So for Montreal, it seems like GFAS and QFED are doing pretty well. CFEPs and GFED not as well. It's sort of a similar situation in Hamilton, so also in the eastern portion of Canada. In the western portion of Canada, it seems like, unfortunately, CFEPs is the one that's kind of the outlier here, that's performing less well relative to the other emission inventories. And then in Vancouver, it's again, GFAS that's doing pretty well, and then GFED is doing relatively well, whereas QFED and CFEPs are kind of far off. So the takeaway message here a little bit is for black carbon, we were missing data, so I wouldn't draw any strong conclusions, but it doesn't seem like CFEPs is doing quite as well as most of the other models. So I just want to quickly summarize some of the important points from my talk. So in general, it seems like GFAS does work quite well, I should say relatively well. So it has the best performance metrics among the different inventories we explored. QFED is pretty similar, so it's slightly worse, and this might be due to the fact that it has this less sophisticated plume parameterization where they take 65% of emissions and put them in the PBL, and the other 35% go above the PBL. I also want to say, okay, so CFEPs was pretty good. When I started the project, I really wanted CFEPs to be the best. I wanted to just like hit it out of the park and be amazing because I had the kind of bias coming into the project. But then in retrospect, it's doing just as well as for PM2.5, it's doing just as well as the other inventories. It's very competitive, let's say. And, I think that's actually exciting, and that's a great finding because, CFEPs is really meant for forecasting. Okay, so they're not measuring fire radiative power because they're looking at fires that are going to be happening, tomorrow or the day after that. And so I think for a model that's really meant for this kind of short-term forecasting, the fact that it's doing just as good as the established inventories that's using historical data that's very good. So that's a very positive finding, I think. And I think GFED, that's something that I think as within the geochem community, maybe we need to look at a little bit and try to figure out a better way to implement GFED into the model, because right now it seems like to me it's problematic. So that's something to be discussed sort of among the geochem modelers. And then finally, for black carbon, all the inventories exhibited a negative bias, but once again, GFES kind of rises to the top. It seems like it's doing a little bit better than the other models. So then just quickly, I know I'm out of time, so I just want to quickly acknowledge, in particular, the Biomass Burning in Canada project. So this is a project in Canada to study biomass burning emissions. There's both modelers and experimentalists. So I want to just thank the whole group. In particular, I want to thank John Abbott, who's the PI of the project, and also Dylan Jones, who's provided a lot of help with the geochem modeling. So it's been a really productive project in Canada for understanding biomass burning. So I really want to acknowledge this both source of funding and source of collaboration. And the other thing I want to quickly say while I have a chance is I have a postdoc position available in my group for studying these sorts of issues using geochem. So it's 2 to 3 years. It's out in Montreal. So if anyone's interested in the position, I haven't started advertising yet. So if you're interested in the position, you have an inside track, you can just go ahead and send me your CV, and I'd be happy to talk to you about this position. So that's it, and I'm happy to take questions.
Sounds great. Thank you so much, Patrick. I just have a quick comment. So for the emission comparison, so the FIN version 2 actually behaves so much better, and that's also why we use work with FIN. And just a really big shout out to Christian and the team. Yeah. Question?
Yeah, for FIN, we would love to use FIN, but we didn't use FIN because it's not available for 2021. So that, and at least for what I mean, if it is available for 2021, let us know because we would like to run it. So.
Yeah, awesome.
Yes, it is.
Yes, the emissions is available actually until 2023, I think, right? Yes.
Okay, I'll have to take a look at that.
Yeah, I really hope we can also put it back to the geochem.
Yeah, I guess that's the thing. It's available, but it's not available currently for geochem. So that's the missing step. Yeah. So if someone wants to take the initiative to do that, that would be awesome. we already moved one emission inventory over, so I feel sort of like we've done our duty. So.
Yeah.
Patrick, this is Shobha. I have a question. It's really puzzling to me the way you set up the experiment. Like when you want to compare the different data sets, why would you vary the plume height? You would want to fix the plume height for all the data sets when you do these simulations, not. And also, I'm not understanding when you say QFED data comes with this plume height. QFED is just an emissions inventory. It doesn't come with plume height information. It's you who determine how you use that, right?
Yeah, I mean, I think the point here is more that it's, there's people who are developing the inventories and there's people who are using the inventories. And I think with the QFED, a priori, we didn't know about this issue, but that's the way it's implemented currently in geochem. So if you download geochem from GitHub and you start running it using QFED, this is what you get. So I think here what we have is not a scientific issue so much as a technical issue that needs to be corrected. So yeah. So I mean, so that's kind of.
I think like our conclusions like GFED has this bias, QFED has this bias. It is unfair to the data sets because you are using different plume rise for different data sets. It's not a fair comparison. Is all what I'm saying.
Yeah, I guess I would say through the lens of geochem. That's a fair comment. Yeah, I understand.
Patrick, this is Jun online. Did you mention the Hamilco module in the geochem has some bugs?
Yes.
Okay.
Yeah. So I mean, this came up. I believe this came up at the last geochem meeting. I wasn't there myself, but people from my group were there, so they were involved in the discussions.
Do you mind? I have somebody to contact you to ask a little bit on that.
Yeah, you can definitely contact me about
okay,
it.
okay,
Or
thank
and
you.
then Robin Stevens in my group also as
Okay,
well.
okay, I'll send you an email then. Thanks.
Yeah.
Hi, Patrick. Max in the room. I was just wondering, you showed the slide with the emission ratios for all of the different inventories, and from your earlier slide in the presentation, it seemed they were all coming from Andre or Akagi, but they all seem to be very different in when comparing all the inventories separately. Can you explain this?
Yeah, I think the difference, that's a good question. This is where it's stretching my knowledge a little bit. But my understanding is, so these are the emission factors. So this is pretty, like I know, for example, for CFAPs, like we're talking about like really like maybe 10 things. So like PM2.5 and maybe some ammonia, things like that, and like CO. And then there's this extra step where you have to speciate those. So that's where I think you're maybe getting some of this difference, is this when you actually take those factors for whatever 8-10 species, and then but then you want to then speciate that out over I don't know 20-30 VOCs, and for example for PM2.5 you have to speciate that between black carbon, organic carbon, and maybe a little bit of dust, for example. And so I think that's where that's another spot where you can start seeing some differences between the inventories.
Hi, Patrick. Shima Shams from NSF Banker. My question is about the creation of inventory that you explained. Can you comment on the live fuel versus dead fuel and the associated moisture and how it was incorporated in the data set?
Actually, I can't. Just to be clear, I meant to say this in my presentation, and I probably skipped over it. The project's goal is really to take CFEPS as it exists already, which is developed by Environment and Climate Change Canada, and then move that over to Geochem. So the actual details of how, for example, here, the fire weather index system works, to be honest, I don't know the details of how that works, but it is described in Carrie's paper, so which is cited here.
Any more questions? Okay, so if there's no questions, we're gonna move on to our next speaker. Thank you so much, Patrick. Thank you.